So this is my attempt to explain expected value. What I'm going to do is do a simulation, and the simulation has got to do with fair dice. So I'm going to go equals rand between, and hopefully that's going to do something for me, equals rand between, oh, it didn't, and I want to go, I think 1 and 6, and we'll just test that. So I've got 6, okay, and I'm going to go across. Right, so if I just hit any old number, can you see what I'm getting there is random numbers between 1 and 6? Yeah, so that's okay. So I'm just going to get rid of that like that, and here I'm going to copy this down. So if I copy it right down, I can keep going. Oh, what will I get there? Oh, that'll do. And actually if I copy it across like that, I'll get even more. So I've got a whole lot of random numbers, okay? So, oops, there we go. So what I'm going to do now is sum. So I'm going to grab all of that, like so. And I'm going to use my summing tool. And then I'm going to, whoops, copy that. So that's, oh, where is my sum? Something bad happened there. So I'll get my sum. Okay, so there was my sum there. And how many times did I throw the dice? Let me see. That was 856. So I could say equals that divided by 855 times. That's not right. Okay. Let's just pause. So I fixed it up, and that here is my count of the number of times I've thrown the dice. Here's my total, and this here, the formula is this divided by that. So that is my average. Does that make sense? My average. Now if I grab these two and I go across like that, then I'll have to do this. Then I can see these different averages for all the times that I've thrown it 355 times. If I hit a key, it'll recalculate. Okay? Does that make sense? So I'm throwing these die, one die, two dice, I don't know, whatever, 355 times, and then I'm doing it once, twice, however many times along here. Let's have a look. 16 times along there. So I could actually sum that and find the average of the whole lot, yeah? So if I go, I won't bother at the minute. Can you see the different numbers? It's changing all the time, yeah? But what was the expected value, the average value of throwing a dice, a fair dice, over a long time? 3.5, nice. Now, if we look at that a different way, here's the dice values, 1, 2, 3, 4, 5, 6. And what's the probability? 1/6. Oops, okay. 1/6, and it's 1/6 the whole way along. Control C, Control V, not my best work. Okay, so how do we find the expected value? Here's the thing. We go here. We can go 1 times 1/6 plus 2 times the probability of getting a 2 plus 3 times the probability of getting a 3 plus 4 times the probability of getting a 4 times 5 times the probability of getting a 6 plus 6 times the probability of getting a 6. What's that going to all add up to? 1/6 of 1 plus 2 plus 3 plus 4 plus 5 plus 6. What do they all add up to?
21.
Is it? So what's 21 divided by 6? 3.5. So I've got there, I had my simulation, and so over a long period of time, my simulation, if I did it enough times, would actually become the theoretical probability. So the theoretical probability is 3.5, but you can see they're not exactly 3.5, are they? But if I was to add all of those up, so that's what I was talking about before, so if I grab, those ones and I sum it, where's my sum thing? Auto sum, okay, and there was 16, so I'm going to take that, so equals my 56 divided by the 16 columns. Now let's have a look at that one. What is going to be different about this one? Is it more variance or less variance than these ones? Less. Why? There's more and more samples. Yeah. So that's cool. So you can see if I rounded that to one decimal place, that would always come to the 3.5, wouldn't it? Okay. Now I've got one more thing to show you. Okay. This is one of my favourite little applets. I just googled it and it comes up. Central limit theory applet, like whatever you want to call it, and just ignore that, and coming down. So I'm going to throw, actually I'll throw one dice once, okay, and I can throw one dice 10,000 times. So rolling one dice is your uniform distribution, okay, uniform. The average of that we know now is 3.5, because 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6 is actually 3.5. Was it? Yeah. Okay, so 2 dice. I get a triangular distribution. Okay, so we are going to be doing triangular distributions. If I'd started with only 1 dice, I just have to re-thingy this. So if I have 2 dice, that doesn't look like a triangular distribution, does it? When you're only throwing 5 dice at a time, doesn't look triangular at all. But if I do 10,000, triangular. So that's your whole thing. If you do lots and lots and lots and lots of dice throwing, eventually it will actually be the same as the theoretical probability. No, it's triangular. This one is more approaching a bell shape, the 3 dice. Once you go to 5 dice, you get the most beautiful bell shape. Okay? Alrighty? I think that's enough for our brains at the minute.